Okay, so I have started the recording and I hope my screen is visible. Okay, I hope my screen is visible. Okay, let me share again. Yes, it is visible and it is moving also. Slides are moving and visible, and I already checked the recording. So my um, video and audio is recording perfectly fine. So today is our ninth lecture. Welcome you all to our ninth lecture, and today is our last lab session of this course, and I will be solving last assignment of this course, which is assignment number 8. And let's wait for a few minutes for others to join. Okay, Shivam wants to join. I'm adding him. Okay, welcome Shivam, welcome Patlika. So let's wait for 5 more minutes to for other people to join. Okay, looks like not other people will not going to join. So welcome both of you, Patlika and Shivam. As I've already mentioned that let me introduce first myself. I am Bhupen Singh, doing PhD under the guidance of Professor Pratik Sen in the Department of Chemistry. As you know, I am a PMRF fellow, so I will be giving my, as you know, that being in a fifth year, it is very difficult to manage all the things, and I'm writing paper, applying for postdoc, giving my open seminar is going to happen on 8th April. So it is anyway, it is a bit of a journey. So today is our last lecture of this course. Hope we will meet somewhere soon in physically or in on any other platform, or might be in NPTEL somewhere somehow. I don't know how, but let's see. So let's start by going through the questions. So the first question is, why is single molecule fluorescence preferred over ensemble measurement for studying protein dynamics? So today we have 20 questions and we have 2 hours. So it's like on an average we will be giving 6 minutes to each question, and 6 minutes are like a good amount of time to solve a question. So I will just today I will just read out the questions, and you will try to solve the question. If you not, I will solve, and even if you solve, I will explain. So so let's start from the first question. Why single molecule fluorescence preferred over ensemble measurement for studying protein dynamics? Answers are Options are: it has higher absorption, it reveals conformation fluctuation hidden in ensemble averaging, it increases fluorescence lifetime, it eliminates photobleaching. Answer is B. Patlika is saying yes. Answer is B. I hope you have understood that it has higher absorption. It doesn't make any sense actually, because molecule is same, no, cross section is same. So if you compare in such a way that the concentration like concentration of the ensemble is higher compared to the ensemble, then you can say yes, of course the higher absorption for ensemble study, but not for the single molecule. But here option is opposite, just opposite to the fact. And B is it reveals conformational fluctuation hidden in the ensemble averaging. So that is true. That is true. Because as sir has already explained nicely in one of the lecture, I hope, okay, I need to share. I need to share my slide first to show this. Is it visible? Okay. So as sir has explained nicely here, see here, sir was talking about this closed beacon. So this quencher molecule is close to the your fluorophore. In this case, it is in open form, it is in partial form. I am not going to explain that, but here, uh, let's say, but all the molecule, all the what sir has tried to say in this picture is that so here only one molecule is there. So here, but in ensemble, lot of molecules are there. So they are like let's say you have like the resolution is so high that you can visualize the single molecule just like that. So in that situation, in that condition, if you see that all the molecules are not coherent, which means that not all the molecules are in this form, closed form, not all the molecules are in open form, not all the molecules in partial form. They are constantly, like going away. These fluorophores are, because they are fluctuating. They are fluctuating. The proteins are having the fluctuations, breathing, liberation, motion. So they have the fluorophore and the quencher have difference, like the distance. It is going and away from the quencher. So so in all the in all the proteins where the quencher acceptor is present, the distance between quencher and the fluorophore might not be the same, and it is not might not be it will not be the same. So that is why it is written here non-coherent conformational fluctuation dynamics. So why conformation? Conformation is because the protein conformation means because of the liberation and vibration motion, liberation and breathing motion of the protein, the conformation of the protein is changing. So that is why it is called the conformation dynamics. But if you have ensemble averaging, like this, so many molecules, which means you are doing the bulk measurement, just like this, you are doing the bulk measurement, then you will not see, you will see basically the average picture of all these. You will not see the conformational fluctuation like conformational fluctuation uh, dynamics of single molecule. You will see the average. So basically, and that fluctuation is so fast that if you do like, you cannot measure basically. That conformational fluctuation intensity is also lost, because then you, after number of, like the concentration is high, so the noise and other things will take over. So that is why this conformational fluctuation the intensity will be much lower compared to, because the concentration is higher. So that is why the signal to noise ratio, if you compare the conformation fluctuation, this signal will be much like less. So in ensemble averaging, you are losing that. So that is why the single molecule, let's say you are focusing on this only this portion. So it is going, this protein is coming and going, and your volume is fixed here only. So then at this position need, so it is also written, a need to investigate a single protein with a time resolution of conformational fluctuation. So basically how you can do that? Just monitor this. Make a volume in a such a way that it's so tiny that only one protein molecule can exist there. So one molecule is coming from left side, and you're reaching to your to your observation volume and leaving. In that way, you can see your like, in that way you can detect the conformation fluctuation timings of the protein. Okay, and so that should be done when the concentration is too low compared to the your ensemble averaging. Okay, so in ensemble averaging, just like in absorption emission, you do like you measure in millimolar. Okay, but here in single molecule you measure the dynamics in nanomolar range. So it is very dilute condition. Okay, so what I was talking about is this one. See from here, if you able to see my cursor, I hope it is visible. uh, it is visible. Okay, because I can see my cursor. So let's say from here protein is coming here. You see this green molecule, this yellow molecule, it is coming here, it will flourish, and then it will go away. But you are focusing somehow in such a way, you are make the instrument in a such a way that it will focus only this part. So only one molecule is coming and going, you are measuring the dynamics of that protein. So that's it, and this is the setup of single molecule fluorescence spectroscopy. So why this? And the turf also, total internal reflection method, you can also measure the single molecule fluorescence. Okay, So given you the little bit idea, I don't know, we have animation. Okay, no problem. No problem. Option B, also solution is written here. So I will be going to share this screen. Okay. Right, I'm presenting now. Yeah, my screen is visible here. Okay. So in the solution it is written in sample measurement, the single signal is the average of millions of molecules. Thus, individual conformation fluctuations are lost. Single molecule spectroscopy reveals dynamic heterogeneity, conformational change, fluctuation kinetics. So I think I have given you uh, uh, enough knowledge to solve this question. So I hope it is clear to both of you. So just give thumbs up or reply in the chat box. Then we will move forward. Okay, Shivam is saying yes, sir. Okay, so I'm moving forward to the next question. Next question is compared to monomer fluorescence, examiner emission generally. Let me check my video. So it is recording. Excimer emission characteristics. Okay, okay. What are the options? Appear as shorter wavelength, it identical to monomer emission, is a broad and red shift, occurs only in a triplet emission. Take your time, solve this, you have time. Yes. Yes, broad and red shifted. Yes, it is correct. So examiner emission characteristics, red shifted, broadband, structureless, structureless spectrum region. The excited state dynamic has a weak bonding and a large vibrational distribution resulting in a broad emission. So I can show you in the first lecture. So let me share this first. Okay. I hope, yes, I can see that I have shared. Are you guys able to see the new shared slide? Okay, okay, fine. So let's see. See this, what sir has explained in this example. Uh, he has taken the example of pyridine and heptane. See here as first here 10 to the power minus 6 molar concentration of this. After that, after doubling the concentration, the intensity at here is increasing. But after increasing the concentration much more than this in a molar range, like millimolar range, this is in micromolar. The intensity is decreasing here. See, the quenching of the band is here from here to here. But another band at the red shift and the broad peak of that emission is coming. New type of emission is coming, which is very broad and red shifted. So why so? Because as Sarah has already explained, see in the ground state it is like 2 pyrene 2 pyrene. It is the case of the dimer formation in the excited state. So in the ground state, like 2 pyrene 2 pyrene, if they are, even if they are like even if we consider that they are bonding, so two electron of 2 electrons are here, 2 electrons are here. So after like combining, like after this bond formation, what will happen? 2 electron will go here. According to the, as we have studied this what the molecular orbital theory. See, 2 electron, 2 electron. So net stabilization is 0. So in the ground state, pyrene cannot form dimer. So that is the thing. But in the excited state, this molecule, this electron is going here, which means what is happening? What is happening? If you see the next net stabilization will be like half of 2 minus 1 plus 1. So it will be what? 3 minus 1 divided by 2. So the bond order, kind of bond order. I should not say bond order. I should say the net stabilization will be there. Net stabilization should not be 0. So that is why the dimer formation is there. Okay. So net stabilization is there. Hence the dimer formation is happening at the excited state. Okay. And as you can, and obviously both of them are forming, net stabilization is there. So compared to the ground state, their energy of the excited state dimer, obviously it will be low because not net stabilization is there compared to your ground state pyrene. So it will be the red shifted, and because of it is not highly the bonding is weak. Bonding is weak. This bonding is weak. That is why a large vibrational distribution is happened. So that is why this the broad peak will you will observe here. Broad emission. Okay. So okay. So I hope you have understood. Fine. Okay, both of you are fine. So I am moving forward to the next question. Next question is, if the diffusion time decreases in FCS, means it is tau d. It indicates What is indicates? Molecular diffuse faster? Molecules diffuse faster? Molecules diffuse more slowly or become larger? Because diffusion time has increased, which means that whatever I have shown, this observation volume, this observation volume, this observation volume here, the molecule is residing for longer time, for longer time. So how can it be achieved? If you increase the viscosity of the solution, so the molecule will diffuse slowly, or or let's say one sample you have monitored, and after that you have somehow denatured the protein, or you have increased the temperature, so your structure protein is getting large. It will take more time to diffuse. So diffusion time increases means molecule diffuse slowly or become larger. So that should be the answer. And C is the fluorescence lifetime increases. That is no way correct. Excitation intensity increases, no. This so solution, you see, tau d is equal to omega divided by 4d. D is the diffusion coefficient, omega is the beam width, waste, and D is the D decreases large molecule. If D decreases larger molecules, tau d increases. Therefore, slower diffusion, larger molecule or binding event. Okay, okay, they are talking about the diffusion coefficient. Okay, no problem. Diffusion coefficient if decrease, increase, no, decrease then of the large molecule, because large molecule is there, then the diffusion coefficient is obviously, it is going slower, coefficient will be low. The diffusion coefficient, if that is low, which means the tau d will be higher. So anyway, everything is intercorrelated. So I hope you have understood. If, and also in such lecture also, let me share this again. In such lecture also, here, see this, sir, I have drawn this. See, one molecule is passing like this. It will take some time. But this molecule is passing from here. It will take much less time. This molecule is going like this, is here and here. It will take much more time. And that fourth molecule is just going inside the observation volume, coming out. It will take the least time. Okay. So that is how you can visualize that for higher time or lesser time the molecule is residing inside your observation volume. It tells that if the molecule is taking much time or diffusion time is increases, which simply means that the molecule is moving slowly or become larger. Okay, so I hope it is well and good. Let me check my, yes, it is recording 30 minutes. Okay, next question is this: in an FCS experiment, diffusion time is 200 microsecond, beam waste is 0.3 micrometer, then the diffusion coefficient is, so this is simple, it is also written there, tau d equal to omega square divided by 4t. Tau d, 200 10 to the power minus, tau d and the omega is also given, micron, 30 micron, you can convert it to the centimeter, and then you can simply know that the diffusion coefficient is Then you can simply calculate the diffusion coefficient, and why that equation it is written in the solution, tau d equal to omega square divided by 4d. So if you calculate it out before calculation, you just make sure their unit are like well and good. So this beam waste you have to uh, convert this in centimeter, tau d in second, then you can calculate the diffusion coefficient in centimeter square per second. So answer is 1.1 10 to the power minus 6 centimeter square per second. So it is option B. Okay. Any confusion, both of you? No, sir. Okay. So I hope everything is good. Let's move to the next question. What about Patlika? Okay, fine. Moving on to the next question. This you need to figure it out first. In an FCS experiment, the detection volume is 0.5 femtoliter. In an FCS experiment, the detection volume is 0.5 femtoliter, and the number of molecule increased is, then the number of molecule measured is 5. What is the concentration? So you know how to calculate the number. So this is the concentration multiplied by volume. Concentration multiplied by volume. It will give you? Number of moles, and multiplied by number of moles to Avogadro number will give you the number of molecules. So this is equal to n. Now you know Avogadro number 6.022 into 10 to the power 23, and what they are asking, what is the concentration? So this you need to find it out, concentration, and n, the number of molecule measured is 5. So this also given 5, and volume is also given 0.5 femtoliter. But before the calculation, you need to convert the units also in femtoliter to liter. Avogadro number is number, and what is the femtoliter? Number is number. Avogadro number and number of molecules is also number. So only the volume unit you have to convert from femtoliter to liter. So the concentration will turns out to be the 16 nanomolar around. Option B. Just the calculation, nothing much. Okay. So should we move forward? So I'm not solving the questions. Like I'm solving the question. I'm giving you the hint, but I'm not like doing the calculation. So you need to do calculation. If you have any doubt, you can write in the portal. You can also comment on my YouTube channel, or like YouTube video, and here also you can ask. I hope it is already submitted, this assignment. No need, sir. Okay, fine, fine, sir. Okay, fine. So I'm moving to the next question. So next question is, if the triplet fraction increases from 0.1 to 0.3, the FCS curve will show reduced fast decay amplitude, larger fast decay amplitude, no change, shorter diffusion time. This you guys need to tell me. I'm giving you around 5 minutes. Think and just don't type B because answer is written, solution is also written. You have to give the explanation, like your explanation in the chat box, so that I can understand that you have understood. It is recording, yes. 37 minutes recorded, no problem here. Any problem? The question was, if triplet fraction increases from 0.1 to 0.3, the SCS curve will show. See, as the equation is written in the solution, it is here in this slide only. So g tau equal to 1 by n, 1 plus t upon t minus 1, e to the power minus tau by tau t in bracket 1 plus tau d divided by tau d to to the power minus 1, where the capital T is the triplet fraction, means like this is the fraction, and T divided by 1 minus T is the amplitude, triplet contribution. Okay, so if you just calculate it, the T, if the triplet fraction increases from 0.1 to 0.3, which means then you can calculate the triplet contribution amplitude. T upon 1 minus T, it turns out to be 0.11 for T equal to 1 and 0.43 for T equal to 0.3. So triplet fraction is increasing from 0.1 to 0.3, which means that triplet contribution amplitude is also increasing from 0.11 to 0.43. Thus, the Faraday amplitude of the autocorrelation curve is increasing. So, option B is larger fast decay amplitude. Yes, it should be like the dip completely increasing or decreases, larger or slow. But anyway, so and tau t in this equation is the triplet relaxation time. And what is the term? Triplet process occurs in microsecond, much faster than the diffusion. Diffusion occurs in millisecond. Thus, fast decay in the correlation curve correspond to triplet breaking. So, as you know that, as I have already explained, that the amplitude of the triplet blinking or triplet contribution will increase. Okay, so option B is correct. Larger fast decay amplitude. Any problem? So Patlika is writing this part is not in the sir lecture. Actually, it is in the sir's lecture. I also. Let's see. 45 minutes recorded. I need to check again and again because last time what happened in one of the lectures that I was teaching, I have already taught for around 1 hour 50 minutes, and after that I have checked, the video was not recorded. So I have again recorded the video, again done like the again I have taught and recorded the video. So it was very hectic for me. So no problem now. It is recorded. Sir lecture, this is the question. Oh, okay, okay, okay. This is the question. Somehow written something very differently. As I can see, it is written in the search lecture. See, this question is. Oh, you are not able to see my this screen. I need to share first. I hope it is visible. Yes, it is visible. Single molecule. Who is coming now? Welcome Chinna Pandiyas. So as I was saying that it is in the here only, or it was in the first lecture. See this equation, because of the animation or something it is not very clear. Anyway, this is very simple. I have given you this also, no? Okay, sir. Now this screen probably this screen is visible probably. Yes. So see this contribution I was talking about, T by 1 minus T. This is the amplitude. Triplet amplitude, triplet contribution का amplitude. Triplet contribution amplitude. And T T T here, T is your triplet fraction. Triplet fraction. That's it. So I guess option B, as I've already explained, there should not be any problem. Okay. Patlekha Sim, both of you are good to go. Okay, moving to the next question. To suppress triplet state blinking in FCS experiment, one typically adds what? Heavy atom, oxygen scavengers, triplet quencher. Example is cyclooctatetraene and salt. So this if you know, you know. This is nothing like nothing science or any formula or anything you need to solve it out. It's just the kind of the effect or information. So triplet quencher is option C, this cyclooctatetraene or this Trolox. So these shortens the triplet lifetime, reduces reduce blinking. Okay, option C, nothing you can do about it, and I also don't have anything to explain about this question. So, or you guys would like to add something, or if you are good to go, then I will move forward to the next question. Just type yes, no, or anything, whatever you want. You just can indicate and then tell me, or write in the chat box. Give thumbs up. Then we will move forward. Yes, sir. Shivam is saying. Okay, so basically you guys are saying that I should move forward, right? Okay, moving to the next question. Next question is, which detector is the most used in the single molecule fluorescence detector? This is also like information. PMT, avalanche photodiode, CCD camera, or photometer, bolometer. So the option is B, avalanche photodiode. This typically used in the single molecule fluorescence detection. Okay, and this is PMT used in if you have like yeah, in such lecture it has been explained also already in your in spectrophotometer and spectrophotometer. And this PMT is work on the principle of photoelectric effect, and that effect is given by Einstein, and he got the Nobel Prize because of this only. But many people know that, like, confused that he got the Nobel Prize because of that equation E is equal to mc square, energy conservation, because that is the most famous and well celebrated in like physics community or chemistry community also. But he got the Nobel Prize because of this photoelectric effect, Einstein. Anyway, that is like the extra information for you guys. So avalanche photodiode advantage: single photon detection, high sensitivity, fast response, thus widely used in single molecule fluorescence activity. So sensitivity is higher, photo detection is also higher, and the fast response. So that is why avalanche photodiode are used in the this single molecule fluorescence detection. Option B. Okay, just again, because this is an interactive session, so I'm expecting you guys to just interact. Thumbs up. Okay, okay, both of you are good to go. Chinnapandi, I don't know about you, but you are not responding. So two of my students are saying they are good to go. I hope you also have understood, and if not, please type, and or also if you want you can speak also. But for now I'm moving on to the next question, which is: a protein binds to DNA, forming a complex twice the hydrodynamic radius. Diffusion coefficient changes approximately to what? So the Stokes-Einstein relation, you know the Stokes-Einstein relation? Any one of you out of three students? Patleka Shivam, Chinnapandi, yes. I can show you. Okay, let me first share my this laptop screen. Already shared. Okay. I hope it is visible. Yes, it is visible. See this Stokes-Einstein coefficient. The Stokes-Einstein equation relates the particle's diffusion coefficient d to fluid viscosity and particle radius, and defined as d equals to kVt divided by 6 pi eta r for sticking boundary condition, or d equal to kVt by 4 pi eta r for slipping. So it describes Brownian motion of spherical particle in viscous medium, linking microscopic viscosity to atomic molecular transport. So anyway, so as we can see, this diffusion coefficient, this is the diffusion, and this is the particle's radius of the particle. Okay, of particle. So let me share my PPT again. Will not take much time. Okay, good to go. See, D is the diffusion coefficient, R is the particle's radius, as I've already explained. So they are inversely proportional to each other. 56 seconds, minutes. Okay. So D equal to, this is inversely proportional, right? D is inversely proportional to 1 by R. So the question was, a protein binds to DNA forming a complex twice hydrodynamic radius, means it was now 2R. Diffusion coefficient changes approximately to what? It will be half, obviously. So option A is correct. All three of you. Is it okay? No response from anyone. Chinnapandi, I want. Okay, Patlika is active. Shivam is also active. Chinnapandi, just give thumbs up if you have understood. You don't have to like speak or write. Just give thumbs up. Just thumbs up. I hope you are able to like listen to me. My screen is visible to you. Your internet is fine because you are my student. So I should teach you. Like you should understand. Otherwise, because I'm investing my time, lot of time and effort, and you are not understanding, then my purpose is not served. Still, you are not responding that much. Okay, so should we move forward? Okay, moving on to the next question. The pinhole is a confocal microscope primarily. The pinhole in a confocal microscope primarily increases fluorescence intensity, blocks scattered excitation light, reject out of focus fluorescence, prevent photobleaching. This you need to answer. I want answer from all of you, all three of you. Take your time and then explain. Like answer and explain. Give your explanation in the chat box. So 1 hour is already completed. And my video is recording. Everything is going fine. So this you need to solve. In another 1 hour, I will be solving previous year's assignment. Hey, welcome Chinnapandi. Sorry, come again. I am not able to listen to you. Are you speaking in English? Yeah, tell me, because your voice is breaking, so that is why I am not able to listen you properly. You can do one thing. See, you do one thing. You do one thing. You stop your video. Hello. You need to like involve in this assignment. You have to solve the question. You can do the other part later because this is the last lecture of this course. So if you have any doubt from previous assignments also, like previous assignments also of this course, you can ask. But that already I have explained. You can go and watch my lectures, and also if you don't want to watch the lecture, you can go to the Google Drive, the log sheet, which I already shared to you by NPTEL team. So you can go there and just check the lectures only, the PDF. Okay, so you are not responding. Just I don't know what the, but okay, try to solve this question. No, 10th. Patlika Shivam, you guys also try. So as I was saying that it is already 1 hour, 3 minutes, and we have still 10, 10 question left. So I will be solving previous year assignment 8 question. So we need to be little bit faster. Blocks scattered light. Blocks scattered light, or it will not pass the light which is out of focus. Sorry. Okay, fine. So it reject out of focus. So I should show you the this. Let me search lecture, PPT or PDF, whatever it is. Mm, see this. This is laser beam. Laser beam is coming here, here, here. This is objective. This is sample. So let's say this point, at this point, it is here. The focus is here. So it is going back dichroic. It will not pass. It will reflect, and this going to this concave mirror. It will converge it to the pinhole. So only these rays which are bold, not dash line, a bold line will pass through this pinhole. Out of focus means even the small change here, focal plane if you change, like this, the focus is changed to from here to here. It is like it is converging. This mirror is converging at this point. So but hole is here, so this ray will not pass from this mirror, this pinhole. So basically it rejects out of the focus fluorescence. Fluorescence is already coming from all your sample because you are exciting that the laser beam is falling on your full sample, whatever volume you have drop casted there. Okay, whatever volume you have kept there, the volume, it is exciting all your molecule, but because of this objective and confocal microscopy, they are converging at one particular point, and that detection volume is very small in femtoliter. So that is why it is only passing only like rays which are on the focal plane. Okay, so I hope this question is okay. Oh, why is my camera is off? How many of you are here? Okay, so today's strength is 3. So option C is the correct answer. It eliminates the out of focus light, improves spatial resolution, and defines detection volume. Thus enables confocal detection. So answer is C. Okay, Patli Khan Shivam and Chinapandi has. Okay, okay. So should I move forward to the next question? Okay, moving on to the next question. Okay, this now question is started from the these questions are from the previous year. Okay, so the first question is, among the following, which factor will most likely decrease the fluorescent intensity of an among the following, which factor will most likely decrease the fluorescent intensity of an XI plate? Okay, so option A is increase in the slit width of the emission monochromator, which will decrease the fluorescent intensity of the XI plate. Increase in the slit width of the emission monochromator. Increasing the slit width will increase the emission. So that is definitely wrong. Increase in the temperature will okay. Increase in the temperature will decrease. How it will decrease, that you have to explain it to me. It will decrease and increase in the excitation light intensity. Increase in the temperature and increase in the excitation light intensity. Increase in the excitation light intensity, that will also going to increase the intensity of the, if you somehow increase the excitation light intensity, but I don't know how to increase the excitation light intensity. but but by changing the power of the light, but how can we change the power of the light? Cutoff filter is there, but let's say you have a fluorometer, how can you change the power? Okay, so as I got to know recently that like one of my colleague, not colleague, well, like I'm still fifth year PhD student, so I would call him. He's he's my collaborator. So we are collaborating our like doing collaboration in our PhD times. So we are trying to publish some paper. So she told me once that by by increasing the or modulating the power of the light by adding the filter or any filters, you can increase or decrease the excitation light intensity. But anyway, it is increasing the excitation light intensity. But increasing the excitation light intensity will will not going to decrease the fluorescence intensity of the excited place. It will only going to increase. So that is also correct, wrong. And increase in the pressure, that is not relevant, I believe so. So your option is correct. Option is B. But you have to give me the explanation. That explanation is also written, but you have to explain and tell me. Read it out first, and then tell me. So same time with increase in the temperature, collision among the molecule increases, which will destabilize the XI place complex. Yes, perfect. So the explanation is here is written as then an XI place excited state complex is primarily sensitive to the environmental condition. So the explanation is an excited state complex is particularly sensitive to the environmental conditions such as temperature, solvent polarity, quenching effect, so the higher temperature enhances non-radiative decay pathway such as vibration, relaxation, collision quenching. Collision quenching occurs because increased molecular motion lead to more frequent intermolecular collision which dissipate energy non-radiatively. In the case of exciplace, which are weakly bound excited state complex, temperature rise may destabilize the exciplace, leading to the faster dissociation into separate excited and ground state molecules. This results in decrease in the fluorescence intensity of an exciplace. Chinnapandi, why don't you mute yourself? I am muting you again and again. You are unmuting yourself. I don't know why. Why are you unmuting yourself? Don't unmute yourself. Again you have. Okay. I'm removing you from the call. One hour, 18 minutes. It is recording. So the answer is already given. Option B. I believe you guys have understood. So should we move to the next question? How much time we have now? Again, someone wants to join, but let me see. So it's 1 hour 18 minute. 1 hour 18 minute means, and it is 5:10. So 8 minutes. So 5:52. I need to stop. Then it will be 2 hour. Okay. So how much time I have now? Like 40 minutes. 42 minutes. Okay. Next question is, which one of the following statement is correct? Excimer is a ground state phenomena, whereas an exciplace is an excited state phenomena. Excimer is an excited state phenomena, whereas exciplace is a ground state phenomena. Excimer, exciplace both are ground state phenomena, both, and D is both are excited state phenomena. This is too simple. Okay. Okay, so I'm typing excimer, exciplace, both excited state phenomena. Yes, you are correct. So excimer are an excimer in a dimeric species formed when two identical molecules interact in an excited state. An exciplace, excited a complex, and exciplace is a complex formed between two different molecules, where one is an electron donator, like donor, and other one is the electron acceptor. Like excimer, exciplace exists only in the excited state and dissociate upon relaxing to the ground state. So option D is correct. So Shivam is typing, but I have no trace of Patlekha in the chat box. So what about Patlekha? Are you there? Okay, yes sir, but tell me the answer of this question. Same sir, what same? I have nothing same. Everything is different. You need to write your answer. Option D. Why option D? Both are excited state processes. Yes, you're correct. So you both have understood. So should we move forward to the next question? Okay. Moving on to the next question. Single molecule fluorescence measurement in a solution. A tiny observation volume can be achieved by both total internal reflection geometry confocal detection. Yes, we have studied studied this in our lecture. So that is correct. Option B is putting two parallel mirrors around the same, tightly focusing the excited laser beam in a solution, reducing the dimension of the sample cell. So option A is correct. So let's see what the explanation is written here. Confocal detection technique uses pinhole to spatially filter out of focus light, ensuring that only fluorescence from a very small focal volume is detected. The laser is tightly focused using a high numerical aperture objective, creating a small excitation volume, femtoliter scale. In turf, the excitation laser undergoes total internal reflection at a glass liquid interface, generating an evanescent wave that penetrates only a few hundreds nanometer into sample. And this selectively excites fluorophore near the surface, minimizing background fluorescence from the molecule deeper in solution. See the last line. This selectively excites the fluorophore near the surface, minimizing the background fluorescence from a molecule deeper in solution. So all this is also like well understood. I hope so. I'm waiting for your response. Okay, Shivam is has understood. Okay, so should we move forward? Okay, moving forward to the next question. In a fluorescence correlation spectroscopy, the usual used detector is this is the repeated question: CCD, APD, thermo, thermopile, PMT. So this is avalanche photodiode. Avalanche photodiode offered a high sensitivity, single photon detection, fast response time, often used in a photon counting mode for detecting weak fluorescence signal. So this is option B. So I hope this is repeated question. I am going to the next question. Okay, next question is the following in a single molecule fluorescence measurement the data from a single observation volume Following is the single molecule fluorescence measurement data from a small observation volume. Okay, the correct statement regarding this is what? Option A, sometimes no molecule is present in a observation volume and sometimes there is a only single molecule is present in the observation volume. Option B, sometimes more than one molecule is present in an observation volume. C, always a one molecule is present in an observation volume. D, number of molecules in an observation volume is constant. The graph represents their time, depends fluorescence fluctuation. The graph represents their time depend fluorescence fluctuation. Okay, you guys need to answer. Take your time and answer. Don't worry, we have 6 questions left and have still 33 minutes. Still 33 minutes. So we will 33 divided by 6. It will be 5 minutes each. So we are on a pace. Any answers from you guys? So any guesses, guys? Any guesses? So the option is A. Sometimes no molecule is present in the observation volume. As you can see, this is off state. This, this time, and sometimes there is a only single molecule present in the observation volume. Intensity is 1. So on all the intensity at each time is same. So one molecule is present in the observation volume. So explanation: the fluorescence fluctuation data suggests that the sometime no molecule is present in the observation volume, then there is no signal is observed, and sometimes there is a only single molecule is present in the observation volume because Ft is 1. So option A is correct. Any doubt? Because I was hoping that you guys should answer, but no, out of both of you, nobody has answered. So again, what to do? I have to do all the things. I have to explain. There is no response from you guys. This is terrible. I know it's Sunday. You are tired. I am tired too. I was playing chess in the morning. See how much I'm doing work at this age only. And you guys are young, younger than me, and still like saying you are tired and all. No, no, no. This cannot be the excuse. You should answer. You should be involved in this. Otherwise, it is very much difficult. It's like one-way traffic. I am just giving you answers and explaining you all, and you guys are just not responding. Like just giving thumbs up and other. You guys are my old students, so you should like answer properly. Okay. After a little bit of scolding, I want to ask you: should we move forward now? Okay. Still we have 5 questions. Still we have how many questions? Hello guys. 5 questions. And we have 25 minutes, which means 5 minutes each question. We have to do it quickly, otherwise we will run out of time. And there will be no class after that. That you also need to keep in your head. If you have any doubt, you need to clarify today. I am your CVR only. Yeah, because I'm saying, because you will not get the chance to interact with your supervisor, like the instructor of the school. You have only me. Okay, so you need to ask to me. You need to ask to me. Otherwise, it would be very difficult for you guys. Or if you don't want to ask here, if you are feeling like there is a hesitation or something, you can ask in the portal. I can answer there also. You can comment in my YouTube video. Ask there. I will I will respond there. Like in one of my video, one or two students like complaining about the questions, that TA of this course, who is making the questions? I'm not making the questions. I cannot do this silly mistake. So TA of this course, who is making the question, is not giving enough time. to prepare the questions, or maybe his supervisor is too busy to cross check. So that is why we have, you have me, you have me. Okay. After a lot of gyan, let's move on to the question number 6. So the question is, below are the two single molecule fluorescence fluctuation data, case 1, case 2, from a small observation volume. The correct statement is, case 1, the fluorescence intensity autocorrelation will decay slower compared to that of the case 2. No, that is not the case, because on state in case 2 is higher. For case 2, the fluorescence intensity correlation will decay faster compared to that of the case 2. Yes, that is should be the correct answer. For both the case 1 and 2, the decay of the fluctuation intensity correlation will be the same. No, that is not correct. The diffusion coefficient of the fluorophore in a case 1 is less than in case 2. Diffusion coefficient. Well. I am not sure about D, but option B should be the correct one. You guys have any idea? Any idea about the option D? I know option B is correct. The diffusion coefficient of the fluorophore in case 1 is less than in case 2. Explanation: when diffusion is fast, the molecule will remain in an observation volume for a smaller time as compared to the case when diffusion is slow. So for case 1, the diffusion is faster as compared to that of the case 2. Obviously, for faster diffusion molecule, the fluorescence intensity correlation will decay faster. Okay, so tau d, this formula tau d is equal to something omega square, I guess, and tau d omega square diffusion, something like this. We have this equation, no? 4d, 4d. So here option B, probably you have understood. What about the option D? The diffusion coefficient of the fluorescence in case 1 is less. So if this is less, which means this is higher. Tau d will be higher in case 1, but this is not the case. Tau d for case 2 is higher. So option D is also wrong. I hope I am clear. Just respond. You guys are like not responding. We have now 18 minutes. 18 minutes. Moving to the next question. 18 minutes and how many questions? Only 4 questions. Okay. So the role of the pinhole in confocal detection geometry of a single molecule fluorescence measurement is. So this you need to answer. I'm not answering. I'm giving you 2-3 minutes. Okay, no reply from you. I'm not able to see any reply from you guys. Also, let me check again my video. It's 1 hour 48 minutes. So now we have only 12 minutes. 12 minutes. 4 questions. 3 minutes each questions. Per questions. 3 minutes. Let's move. So the role of pinhole in a confocal detection geometry of a single molecule fluorescence measurement is to suppress high fluorescence intensity, no. To create tiny observation volume and suppress the background noise. Background noise I would not say, but to cut off the signal from the cut off the signal or block the signal from the off plane. Where one question was there, no? Yeah, out of focus fluorescence. Reject out of focus fluorescence. Okay, and C is to create a tiny focus, tighter focus of excitation laser to restrict the motion of diffusion molecule. No. So option B is correct. To create a tiny observation volume and suppresses the background noise. The combination of high numerical aperture objective and a pinhole leads to the femtolittle scale detection volume and out of focus fluorescence from region above or below the focal plane is blocked. That is what I was saying. Fine. I've already shown you this diagram from such lectures. So this was simple. Okay, Shivam Patlekha moves. Can I move forward now? Because we don't have much time. Only 10 minutes are left and I need to finish 3 questions. Okay, I am moving to the next question. In a fluorescence correlation spectroscopy, the fluorescence intensity correlation G tau is plotted against lag time T, where T0, the autocorrelation is referred to as G0. Autocorrelation is referred to as G0. Consider 3 different solutions of a fluorophore having different concentration. The corresponding G0 value are given below. The corresponding G0 values are given below. So for fluorophore concentration C1, solution C1, G0 is 2, solution 2 is 1, solution 3 is 0. But the correct concentration order is, this is 2 Eg. This is 2, 2, 2 Eg. So Z0, Z tau equal to 1 over, that proportional to 1 by number of n. So if this is G0, it is 1 by n. This is 1 by n, G0. So just correlate. This number is number of molecule. Number of molecule is particle. Means the concentration. Nothing else. So the correct concentration is C3. C3 is greater than C2 is greater than C1 because the G0 value is lower, 0.5 only, which means that the is equal to 1 by n. N is much higher, which means the concentration is higher. So C3 is higher. So that should be the answer. So option D, C3 is greater than C2 is greater than C1. That should be the correct answer. Any doubt? Okay, fine. So I am reading the explanation. According to the autocorrelation function, G0 is inversely proportional to the number of molecules and also the concentration. So higher is the G value, lower will be the concentration of the solution of the fluorophore. Hence, the correct order of the concentration will be C3 is greater than C2 is greater than C3, C1. This is too easy, too easy, too easy. Patlika and Shivam, all good to go? Okay, I am moving forward. Next question. Now we have how many questions left? Only two questions. How many minutes? 8 minutes. 4 minutes per question. We are in the on the pace. From the beginning we are maintaining the pace. From the beginning. That is the beauty of the time. And when you have power, when you have discipline, you can maintain the pace and speed. Okay? And that will be my last class of this course. Probably we will meet again on some other like on other website portal for other purposes. Maybe physically we can meet, but for now, after these two questions, we will say goodbye to each other. Okay, coming to the question. Two fluorescence intensity fluctuations data from the SCS setup as a function of time are given below. Case 1, case 2 is for a protein, case 2 is for a dye molecule. The addition fluctuation of a fluorescent intensity for case 1 is due to the additional fluctuation of fluorescent intensity for case 1 is due to what? Very small observation volume in case 1 compared to case 2, that is not correct. Large size of the protein molecule, that is also not correct. Conformational fluctuation of the protein leading to quenching of the fluorescence. Conformational fluctuation of the protein leading to quenching of the fluorescence. Yes, that is possible because the time is in millisecond, not milli. This is in microsecond. Huh? No. This is in millisecond, and the conformational fluctuation dynamics is in microsecond. So these can be from the conformational fluctuation of the protein, which are leading to the quenching of the fluorescence, and these two diffusion coefficient of the protein. No. So option C is correct. And the explanation for this is the addition of the fluctuation of the fluorescence intensity for case 1 is due to the conformational fluctuation of the protein leading to the fluorescence quenching by the electron rich amino acid. Okay. Of the protein, conformational fluctuation of the protein leading to, for the case 1 is due to the conformational fluctuation of the protein leading to fluorescence quenching by electron rich amino acid. So basically if you are measuring the tryptophan amino acid, let's say you have laser of 290 nanometer or 295 nanometer, then you are exciting the tryptophan. The tryptophan is with some amino acid. If they are electron rich, they can interact with your tryptophan, then your fluorescence intensity will quench. And how they can interact with they are interacting because constantly this protein is in liberation motion and this breeding motion is there. So that is why the electron rich moiety, just let's say for histidine and other, they have the conjugate this benzene ring, so the electron rich amino acid will come close to this and will go away, come close to this and go away. So if they are coming close to it, maybe it will quench, and as soon as they are far apart, the intensity will recover. So something like this. Okay. So the time scale of that is lesser than the diffusion time of the whole protein. So that has to be the fluctuation of the protein. Any problem? Option C is correct. What about Shivam? 57. We have how many minutes? 2 minutes left. 2 minutes, one question. See how disciplined we are. Last question of this session, of this course. Give it a shot. One of the reasons for single molecule fluorescence blinking is, tell me, one of the reasons for single molecule fluorescence blinking is internal conversion, intramolecular vibration, redistribution, intersystem crossing, vibrational relaxation. So the answer of this question is intersystem crossing. ISC. Why ISC? Tell me the answer. Tell me the explanation. Fluorescence blinking is a single molecule measurement, is mainly due to the triplet state formation. So when this triplet state form happens? Because of the formation via intersystem crossing. If you remember, one of our, so answer of this question would be C, intersystem crossing. Okay, this. So as one of the, in one of the question I was calculating the amplitude of, yes, this question only, amplitude of the triplet contribution. See, triplet formation, triplet relaxation time. So this blinking comes because of the triplet formation from singlet to triplet. So that is why this mainly, this process, this blinking is happen because of the intersystem crossing. That is the question. That is the question. Okay. So the end of this course. I hope I made you learn something. I taught you something. So it's been a 19, like 9 lectures, 18 hours. So I was teaching you for 18 hours, and now now time has come to say goodbye to each other. That's, I don't want to say goodbye because I want to teach. I love teaching, and you guys are also like good student. But what we can do? Everything has come to an end. So for now, I'm closing the session. Bye. Thank you for joining the lecture. See you.